November 24th, 1943, Mackin Atoll. At 0510 hours, a single torpedo from Japanese submarine I-175 struck the USS Lyscomb Bay, Casablanca-class escort carrier CVE-56, directly beneath her bomb magazine. 23 minutes later, she was gone. 644 men died in the explosion, including Rear Admiral Henry Mullenix. The crew had nicknamed these ships Kaiser's Coffins, for good reason. Post-action analysis revealed the fatal flaw: virtually no splinter protection around the bomb storage. When that torpedo detonated, the shockwave sent fragments directly into stacked ordnance. The resulting secondary explosion literally tore the ship apart from the inside. This wasn't bad luck. This was predictable physics meeting inadequate armor, a design compromise that the Navy knew existed but accepted to maintain production speed. One single loss drove urgent modifications across the entire Casablanca-class, converting outboard compartments into liquid protection systems. To understand why 644 men died that day, we need to go back to 1941, when America faced an impossible problem: build carriers faster than Japan could sink them. By early 1942, the U-boat crisis in the Atlantic had reached critical mass. Merchant convoys were being slaughtered, and the Navy faced a brutal arithmetic problem. Fleet carriers took over 2 years to build. The war would be lost before they launched. Enter Henry Kaiser and his civilian shipyards, mass production specialists who'd never built a warship. Their solution was radical: convert the construction process itself into an assembly line. Escort carriers could be delivered in 3 to 6 months, but this speed demanded technical compromises that would make any naval architect wince. The critical bottleneck was gear cutting capacity. The United States only had so many precision machine shops capable of producing reduction gears for steam turbines, and every set was allocated to fleet carriers and destroyers. There simply weren't enough gears to go around. So the Navy pursued 2 parallel designs. The Bogue-class, 11 ships converted from existing C3 cargo hulls, got the turbines because the hulls were already built. The Casablanca-class, 50 purpose-built escort carriers, would use old-fashioned reciprocating engines. Noisy, vibration-prone, but crucially, they didn't require precision gears. The Bogues hunted U-boats in the Atlantic. The Casablancas provided air cover for every major Pacific amphibious assault. This was industrial warfare. Quantity was a quality all its own. These strategic requirements created 2 fundamentally different approaches to the same problem, and the engineering solutions reveal everything about wartime priorities. Let's talk machinery. The Casablanca-class, CVE-55 through CVE-104, used 5-cylinder Skinner Uniflow vertical quadruple expansion reciprocating engines. If that sounds archaic, it was. These were essentially enlarged versions of the engines that powered Liberty ships, operating at a maximum boiler pressure of just 285 pounds per square inch. For comparison, fleet carriers ran over 600 pounds per square inch. The result? 19 knots maximum speed, and that's if everything was working perfectly. But the real problem wasn't speed, it was vibration. Reciprocating engines pound. Every stroke sent shock waves through the hull, and that constant hammering played havoc with the sensitive anti-aircraft director's topside. Fire control solutions degraded with every engine revolution. Armor? Forget it. Splinter plating around control stations and torpedo stowage. That was it. After Lyscomb Bay, the Navy frantically converted outboard compartments into liquid protection systems, filling them with oil and water to absorb torpedo shockwaves. The trade-off? Reduced magazine capacity for marginal survivability improvement at best. The Bogue-class took a different path. CVE-9 through CVE-21 used Allis-Chalmers geared turbines, producing 8,500 shaft horsepower. Not impressive by fleet standards, but reliable, critical for extended Atlantic patrols hunting U-boats. These ships were converted to C3 cargo hulls, commercial designs adapted for war, but their turbine plants gave them endurance the Casablancas couldn't match. Now compare both to the Essex class, the standard every carrier was measured against. 8 Babcock and Wilcox boilers feeding 4 Westinghouse geared turbines. Total output? 150,000 shaft horsepower. That's 17 times more power than a Casablanca. Speed? 33 knots, letting them keep pace with the fastest battleships in the fleet. Standard displacement, 27,000 tons. Full load, nearly 37,000. But here's what separated the Essex from every other carrier: the Hangar Deck Strength design. The Hangar Deck itself was the ship's structural strength deck, armored with 2.5 inches of special treatment steel. This created an armored umbrella over the magazines and machinery spaces. The flight deck above, unarmored wood. If a bomb penetrated, it went through teak wood, not structural steel, and the explosion vented upward instead of tearing into the ship's vitals. These weren't flaws, they were calculated trades between speed, protection, and production capacity. These engineering choices weren't theoretical. In the Atlantic and Pacific, they determined who lived and who died. The Bogue-class proved their worth in the Atlantic starting in 1943. Their mission evolved from defensive convoy escort to offensive hunter-killer operations, dedicated U-boat hunting groups that systematically swept designated search zones. TBF Avengers, equipped with ASV radar pods, could detect surface submarines at night or in weather that would have blinded visual search patterns. The geared turbines that seemed modest on paper delivered something more valuable than speed: reliability. These ships could maintain extended patrols without mechanical failures pulling them off station. The results speak for themselves. Bogue-class groups accounted for a significant percentage of U-boat kills after 1943, strangling the Wolfpack threat that had nearly severed the Atlantic lifeline. June 19th and 20th, 1944. The Battle of the Philippine Sea, what pilots would call the Great Marianas Turkey Shoot. This wasn't just an American victory, it was a demonstration of radar warfare. The Essex-class carriers deployed 2 complementary systems: SK air search radar with detection ranges of 75 to 100 nautical miles, and SM fighter direction radar operating in the microwave band, providing the critical altitude data that earlier systems couldn't deliver. The Japanese launched massive strikes and walked into a killing zone. Combat air patrol fighters were vectored into perfect intercept positions before the enemy formations ever appeared visually. 476 Japanese aircraft destroyed, against 123 American losses. Carrier warfare had fundamentally changed. This wasn't about luck or individual pilot skill anymore. It was about systems integration, radar detection, radio communication, and fighter direction working as a unified whole. The carrier had evolved from a platform of chance to a system of precise interception. The Casablanca-class paid for their engineering compromises in blood. Lyscomb Bay we've covered. Gambier Bay went down under surface gunfire at Leyte Gulf, the only American carrier sunk by naval gunfire in the war. Almani Bay was destroyed by a kamikaze off Luzon. But here's the paradox. Their vulnerability was acceptable because of their numbers. A single fleet carrier could carry 90 to 100 aircraft. It took 3 or 4 escort carriers to match that capacity, but they could be built in a fraction of the time. At Tarawa, Saipan, Iwo Jima, Okinawa, every major amphibious assault had Casablanca's overhead, providing sustained close air support. Lose 1, and 2 more were already in the pipeline. And then there's Yorktown, CB-5, not the Essex-class ship. After Coral Sea, she limped into Pearl Harbor with a 250-kilogram bomb hole punched through 4 decks. Admiral Nimitz gave the shipyard 72 hours. 1,400 workers attacked that ship. They welded massive steel plates directly over ruptured hull seams, faster than riveting, but you'd never pass a peacetime inspection. 3 boilers stayed cold. Couldn't fix them in time, limiting her to 20 knots. Electrical wiring was jury-rigged through passageways just to get the flight elevators and radar operational. But here's the detail that mattered. The fuel officer drained the upper aviation gasoline lines and flushed them with carbon dioxide. When Japanese bombs hit Yorktown at Midway, those inert lines likely prevented the ship from exploding like a fuel depot. The philosophy wasn't full restoration, it was just enough to fight. The numbers don't lie. Radar won the Turkey Shoot, numbers won the Atlantic, and welders saved Midway. These weren't isolated victories. They represented a fundamental shift in how naval warfare was conducted and how carriers would evolve. The escort carrier concept proved something that would reshape naval procurement. Mass production could overwhelm qualitative advantages. Kaiser's methods, modular construction, civilian labor, acceptance of technical compromises, became the template for post-war emergency shipbuilding doctrine. The lesson wasn't subtle. Strategic bottlenecks like gear cutting capacity drive design decisions more than ideal engineering ever will. Radar integration became non-negotiable. The SM fighter direction radar from the Essex class evolved into post-war CXAM systems, which directly led to the Aegis combat system on modern carriers. Carrier warfare had permanently shifted from visual to electronic. Task force composition changed accordingly. Radar picket destroyers, electronic warfare aircraft, dedicated fighter direction centers. The carrier wasn't just a floating airfield anymore. It was the center of an integrated sensor and weapons network. The armor philosophy divergence tells its own story. The U.S. Hangar Deck Strength design, unarmored flight deck, armored hangar below, proved far more adaptable than the British flight deck strength approach. When armored flight decks absorbed bomb hits, the kinetic energy transferred directly into the hull girder, causing permanent structural deformation. HMS Illustrious and Formidable were scrapped in the 1950s with irreparable damage. Meanwhile, Essex-class carriers served into the 1990s, repeatedly modernized because their basic structure remained sound. The lesson? Flexibility and repairability trump absolute protection. Damage control doctrine underwent revolution. After losing Lexington at Coral Sea, the U.S. Navy made firefighting a basic skill for every sailor. The handy-billy portable pump, fog nozzle systems, these became standard equipment worldwide. USS Franklin absorbed 120 secondary explosions and 800 casualties at Okinawa and survived. Compare that to Japanese carriers, where damage control was fragmented between engineering and deck departments with no cross-training. The difference in survivability wasn't subtle. Not a single Casablanca-class ship was preserved. They were built to be disposable, and they were disposed of. The Essex-class survivors, Yorktown, Intrepid, Hornet, stand as museum ships today precisely because they were built to adapt. These weren't just wartime improvisations. They became the blueprint. In part 2, we'll examine the British armored carriers, Japanese fleet carriers, and the design philosophies that led to catastrophic failures and unexpected survivals.